My audio and screen is right for you.
Yes.
Okay, thank you. Yeah. So can I start? Yeah, okay. So
Yes.
I'm Akhilesh Nair. So I would be presenting our work on improving subseasonal prediction skill of NorCPM using soil moisture assimilation. So to be specific, in this title, we have three keywords. So maybe I'll try to take up my laser pointer. So we have subseasonal predictions, NorCPM, and soil moisture assimilation. So to start with, let me take you to what is NorCPM, which stands for the Norwegian Climate Prediction Model. So we have a system which relies on a fully coupled Norwegian Earth system model where we contain which has atmosphere, land, ocean, and ice components. So we have a fully coupled model, and we have an ensemble flow dependent ensemble Kalman filter approach, which is strongly coupled to assimilate ocean and sea ice components. So basically we assimilate SST and sea ice into the model, and the ocean component or ocean constraint component works fairly good, and it does its work for what it is designed. So we have a long-term climate reanalysis product, as well as we have a skillful and reliable climate prediction for seasonal timescales as well as annual to decadal timescales. Now, when the second title in my keyword, the second keyword in my title was subseasonal forecast. So let me take you to a small flowchart over here, or representation of graph, where the x-axis represents time or the lead time, and y is the predictability, and different components are shown here, which includes the atmosphere, land, and ocean. So if we check on the time scale between 2 weeks or a week to a month, we can see the predictability is mostly the major component which plays on the predictability is land. So in our system, what we are constraining only till now was the ocean component, which comes from here. So we would be having a decadal predictions. But when we are going on to a subseasonal forecast, we need to have a better land component. And as we could see from different presentations from the beginning of this session, we had different variables on land. So now why we selected soil moisture is because soil moisture is one of the crucial prognostic variables in land surface model, which governs or controls the water and energy exchange between soil and atmosphere. So to fill up this gap in our model with the subseasonal forecast skill, we are trying to develop a land data assimilation in Norwegian climate prediction model. So we have the Norwegian Earth system model, and the land model which is used in NorESM is CLM. So, and the assimilation for NorCPM is done on a monthly scale with anomaly based approach. So we do an anomaly assimilation on ocean component, but on land we know that soil moisture has very low memory. It starts from few weeks to a month or two. So we can't really go on a larger assimilation window, or we can't go on a monthly assimilation. So we need to have daily or sub-daily assimilation, which would be better to capture the diurnal variability of soil moisture. So considering this scenario, we have generated an offline assimilation system using Nor ESM, which is named as NorCPM land. So in this system, we would be forcing the CLM land model with historical run of NorESM run, which would be a fully coupled model run with CMIP 5 forcing, and we would be having 30 ensembles from this scenario. So we have 30 different forcing data to run CLM, and we use ESA CCI soil moisture data sets because we had to create a longer reanalysis product, and the only like much of the reliable reanalysis product we would be getting it from ESA. So we are using a daily assimilation using a flavor of ENKF approach. To be specific, we are using ensemble Kalman smoother approach. So where we update the mean of ensemble and the covariance is updated by ENKF approach. So using this approach, we are assimilating soil moisture on daily scale, and before assimilation we do a CDF monthly CDF matching technique to correct the bias in CCI observation and CLM soil moisture. So with this approach we would be having two test cases or two scenarios. The one would be without assimilation soil moisture, which would be predicted by just the CLM, which would be named as open loop, and one is like the assimilated soil moisture product from CLM. So this is my first part of the results which I would be discussing. But in second part, what we do is we use this land reanalysis product to initialize our NorCPM, which would be named as NorCPM land, and we try to produce hindcast for lead time starting from 0.5 months to 4 months. So we are checking how the improving land condition impacts the hindcast scenarios. So we would be having two test cases again in this, which would be one with the NorCPM conventional scenario and one is with the improved land. So to highlight whatever would be the variation in results from the hindcast scenarios, it would be caused only because of variation in land. So let me take you to the first results. So we are evaluating the land reanalysis results where we have 40 years of land reanalysis. We try to first evaluate it with independent soil moisture in situ observation from ISMN, International Soil Moisture Network. So here on the left side we have a free run case where there is no assimilation, and we could see that there is high error in NorCPM soil simulated soil moisture, and this is the reduced RMSE, that is reduction in the RMSE after soil moisture assimilation. So we could see that the majority of regions show a decrease in the RMSE values, and the spatial mean has a reduction of around 10.5%. We again like evaluated the results with different observations or different reanalysis data sets. So we could see that the free run has had the higher RMSE almost for every continent, and the assimilation of soil moisture, that is NorCPM land, has reduced the RMSE over majority of the regions. Then we check the anomaly correlation coefficient with EIR land soil moisture data. So on the top left, we have here the anomaly correlation from free run, which is open loop without assimilation. And right side bottom, we have here the correlation from NorCPM land, and the green dots are the points which have significant correlation. So we could see that the free run has very few significant correlated points, as well as the blue is like good points. So we could see that over the free there is low points and low significant points, but after assimilation it has fairly increased. And to be specific, when we are talking about land atmosphere or soil moisture atmosphere interaction, the global hotspots lies over the US, Sahel and India. So we could see the improvement over the Indian region as well as, but not in this case, but when we checked with the unbiased RMSE value, we could see the improvement over there. Then we were interested in checking how it affects the land atmospheric coupling. So here, just to highlight, I would be showing the relation between soil moisture and latent heat flux. So when the soil is wet, we would be having higher latent heat and the planetary boundary layer would be low. When it gets dry, you get more sensible heat fluxes, which causes the rising of boundary layer, formation of clouds, and again precipitation, and you get an increase in soil moisture. So soil moisture even affects the latent and sensible heat fluxes. So we tried to evaluate how it changed after assimilation. So here we have the atmospheric coupling index, which is covariance of latent heat and precipitation divided by the standard deviation of latent heat flux. So the reference is used from ERA land, and on the center we have NorCPM land, which is after assimilation, and at the bottom we have the free run, where we could see that there is less coupling, and after assimilation it almost matches with the ERA land data sets over India, we could see specifically, which was not visible in the free run. So with this, we tried to have an hindcast scenario where we are trying to initialize the run at 4 times a year on January 15, April 15, July 15, and October 15. And we run the test case with two initial conditions. So one is NorCPM conventional and one is just changing it with the NorCPM land. So whatever would be the change in improvement or the changes in the simulations would be caused by an improved land condition scenarios. So for this first case, we tried to check how the initial condition affects or what would be the soil moisture memory. So here we are trying to find out the correlation between the difference in soil initial soil moisture and the predicted soil moisture. So we could see that at 0.5 month, that is at 15 days, maybe roughly around 15 days, the initial soil moisture condition is highly correlated with the predicted soil moisture, and as soon as we increase the lead time, the correlation decreases. So on the right side here we have a plot of spatial mean. So we could see that at 0.5 month lead time the correlation is 0.4, but at 3.5 it's almost negligible, like 0.06. So with this, we tried to check what would be the impact on 2-meter temperature, predicted 2-meter temperature. We evaluated the decision RMSE with ERA 5 as a reference. So the top row represents the results for results for 0.5 month lead time. So this shows the NorCPM RMSE, and right on the left we have NorCPM, the conventional one, and right you have NorCPM land. So we could see that there is reduction in RMSE. So blue are the regions where we see the improvement. So we could see that the improving soil moisture is even improving the temperature scenarios. Then we checked how it affects the precipitation. Again, on this we have the first row represents NorCPM simulations. The left row represents the NorCPM simulations. Right, we have the NorCPM land. And first row is for 0.5 month lead time, and the bottom one is 1.5 month lead. So we could see that at 0.5 we have considerable improvement in precipitation at the central US Sahel region and at central Indian region. So we could see that improving soil moisture conditions are also improving the precipitation values, and the precipitation values here are at mm per day. The unit is mm per day here. So we were checking how it affects the soil moisture and planetary boundary layer. So which evaluated how the change in initial conditions. Suppose this is like we are increasing the soil moisture by around 5 to 20%. The temperature decreases on those particular regions. Because of decrease in temperature, we could see that there is change in the planetary boundary layer, and this affects the wind velocity potential. So we could see that there is change in the Walker circulations, and then finally which even changes the precipitation pattern. So with this, I will just, considering the time constraint, I am just running through my slides. So finally, the summary would be that we could prove that improving the soil moisture condition has made it possible that we could improve the subseasonal forecast skill. And one of the major drawbacks of this study was that we have used unconstrained atmospheric scenarios to run the offline CLM run. So we would be going it with the atmospherically nudged or constrained atmospheric constrained forcing data to run CLM. And finally, we would be going up with assimilating different land surface variables such as snow and temperature. And we would be even going with near real time predictions, or we would be assimilating near real time products from SMOS. Yeah, thank you.
Thank you very much, Akhilesh. It was very clear. The impact on precipitation is quite impressive.
Yeah, yeah.
Um, I was wondering, you mentioned that you used ERA land. Do you mean ERA interim land or ERA 5 land?
It's era file land. Yeah,
Okay, good.
yeah,
Perfect. Let me look at the chat. I don't see questions yet in your pad,
yeah,
but I have myself other questions. For the CDF matching approach that you're
yes.
using, you say that it's a monthly CDF matching.
Yeah, yeah.
On which period did you compute your CDF matching coefficients?
So it's for the entire 1980 to 2019.
Okay.
Yeah,
And so do you use um,
point wise.
climatology of this monthly CDF matching, or does it evolve through the years?
No, it's the climatology. It's not
Okay,
dynamically done.
okay,
So
good.
we are even planning to have a dynamic flow dependent kind of CDF mapping approach. Yeah.
Mhm. So checking if anyone has a question, don't hesitate to put it in your pad.
Yeah.
Well, I have more questions, but I don't want to take all the space.
I
So,
think I don't see any questions on you.
because I have one more,
Yeah,
if I
I got one. Is
okay, there is
there?
one here. Okay. So great talk. Is there any particular method you apply to calculate skin temperature and humidity for boundary conditions before the assimilation of soil moisture?
No, I guess since it's a coupled model, we don't explicitly do the boundary conditions for temperature. So we are just updating the soil moisture 10 soil layers of CLM, and it just propagates into the temperature profiles.
And at the end of your talk, you say that you will analyze all other variables related to snow and soil temperature.
Yeah, we are planning because we would be interested in higher latitudes. So currently for soil moisture, we observe that the improvements are mostly constrained to the mid latitudes.
And which observations are you planning to use in?
So it would be snow cover fraction.
Okay.
Yeah.
Okay, thank you. So I think we can close here.
Yeah. Okay.
Thanks again.